While human learning relies on intuition, an artificial intelligence operates through a rigid, iterative process of mathematical optimization. We measure the success of this process using a loss function. This mathematical scorecard calculates the system's exact error rate based on its current configuration. This graph represents a loss function. Training a model requires the system to plot a path down this curve until it reaches the absolute bottom, the state of minimum error. On a simple two-dimensional curve, the location of that minimum point is obvious to any observer. If an algorithm only balanced one or two variables, optimization would be trivial. But to perform complex tasks, an AI must navigate a mathematical landscape far more complex than a single curve. Modern neural networks process data using millions or even billions of individual parameters working simultaneously. Every parameter adds another dimension to the mathematical landscape. This creates a space so dense that humans cannot visualize it, and computers cannot render the entire shape at once. From the algorithm's perspective, finding the lowest point of error is like being dropped into a fog-covered mountain range while completely blindfolded. Without a method to sense the slope of the ground beneath its feet, the system would wander randomly, never improving its performance. Curiously, multivariable calculus provides the specific tools necessary to give a blind algorithm a literal sense of direction inside this high-dimensional space. The foundational tool for navigating this terrain is the partial derivative. To calculate a partial derivative, you hold millions of variables constant and measure the slope of the landscape along a single direction. Measuring the slope along the next axis requires an entirely separate calculation for that specific direction. Once the system computes the partial derivatives for every parameter, it collects them into a single structure called the gradient. Geometrically, the gradient acts as a mathematical compass. At any point in the landscape, it points in the direction of the steepest upward slope. To minimize error, the algorithm calculates this gradient and takes a step in the exact opposite direction. We call this gradient descent. Repeating this calculation turns a random search into a calculated step-by-step descent toward the valley floor. Deep neural networks are built from sequential layers, meaning they function as mathematical functions wrapped inside other functions. As these equations show, calculating the loss gradient from the final output back to the input in one step is impossible. The multivariable chain rule breaks the derivative of a composite function into smaller pieces, allowing the system to process the network layer by layer. This is the mechanism for backpropagation. The algorithm passes these chained calculations backward through the network to assign the exact proportion of error to each individual parameter. In complex terrain, the Hessian matrix provides second-order derivatives that define the local curvature of the space. This information allows the system to adjust its step size for higher efficiency. These principles of multivariable calculus allow a deep network to update its parameters and learn from its data. These topographical coordinates represent the actual architectures behind facial recognition, real-time language translation, and self-driving cars. Every time an AI makes a correct prediction, it is because it successfully navigated a high-dimensional loss landscape to reach a minimum point. The system operates without human intuition or biological intelligence. Artificial intelligence functions as a system of complex geometry scaled across massive computational power. Multivariable calculus is the engine that drives the algorithm down the mountain, turning raw data into simulated intelligence.